Okay, so the title of this section is Wasserstein metric and entropy, but our goal here will be twofold. Okay, our kind of main motivation will be to prove the following so-called Gaussian concentration inequality. Okay, which is the following result, that if you have a Gaussian probability measure P, so this is just our usual centered Gaussian distribution with covariance C. Okay, and this is a distribution on Rn. Then if you take a set of measurable set of positive probability, okay, then we have the following result, that the probability of all the points x which are at a distance from this particular set A, at least some positive number t, is bounded by 1 over the probability of A e to the minus t squared over 4 times the largest eigenvalue lambda maximum of this Gaussian, of this covariance matrix C. This particular constant 4 here can be improved to 2, so this will be an artifact of this particular proof. But the meaning of this result is the following, that if you start with a set that carries some weight, so probability of this set is strictly positive. So let's say we have some set A here on Rn, and then you consider a T neighborhood of this set. So all the points at the distance T from this set, and then you're interested in the probability of the outside of this set, and according to this inequality that we are going to prove, right, the probability of this outside of the set is bounded by this exponent, so constant 1 over the probability of the set, which just reflects the fact that if the probability of the set is small, it will take a little bit longer for the weight to accumulate. But the main feature of this result is that you have this very fast decrease of the probability of the outside of the neighborhood of a set, right? This probability decreases exponentially fast, in fact, e to the minus t square rate with some constant. So this will be kind of our motivation, and the proof of this result will involve various interesting inequalities and objects that sort of come together in one place. So our kind of second goal here is to present or introduce such inequalities as Brunkowski Inequality, Prekopa-Landler inequality. Okay, and also introduce this concept of entropy, and in particular in the proof, what will be useful to us is this variational representation for the entropy. Okay, so before we get to the proof of this Gaussian concentration inequality, we'll first have to discuss all of these results that will be used in the proof. Okay, so let's start with the Brunkowski inequality. And first, let's state this Brunkowski inequality on the real line. Okay, so if you consider a Lebesgue measure, now here we will denote Lebesgue measure by gamma. Okay, in this particular case, this will be on the real line. And then we consider two sets, A and B, which are non-empty. So A and B will be some non-empty Borel sets. Okay, and we will denote by A plus B the sum of the sets, in the sense that it's the sum of all A plus B, where A comes from the set A and B comes from the set B. Okay. And then Brutebinkowski inequality on the real line says that the Lebesgue measure of the sum of A and B is greater or equal than the sum of the Lebesgue measures of these sets. Okay. Now notice that in this statement, this condition that the sets are non-empty is very important. That if one of these sets was empty, then the sum would also be empty, and the inequality would not be true, because you would have 0 on the left-hand side, but you could have some positive number on the right-hand side if one of the sets is non-empty. Now, the proof of this result on the real line is surprisingly elementary and straightforward when you organize it in the right way. And so I'm not going to go over this here. So I will leave this to the notes and go to the next result, where this Brutebinkowski inequality on the real line will be used. Okay. And in fact, this will be one of the main results that we will need in the proof of this Gaussian concentration inequality that we will present. Okay, and this is the so-called Prekopa-Landler inequality. Let's consider some non-negative functions on Rn, real-valued functions on Rn. So suppose that these three functions, let's call them W, U, and V, on Rn into the positive half line are Lebesgue integrable. So in addition to being non-negative, they also should be integrable with respect to the Lebesgue measure on Rn. Okay, and let me say that we will denote sometimes integration with respect to the Lebesgue measure gamma on Rn also simply as a dx. Okay. We assume the following condition on these three functions, namely that for some parameter lambda between 0 and 1, we have the following inequality, that the function W evaluated at a convex combination lambda x plus 1 minus lambda y is greater or equal than this first function u of x to the power lambda and the second function v of y to the power 1 minus lambda. And this is true for all points x and y in Rn. Okay. So this is the assumption on these three functions, and then the conclusion is the following inequality between their integrals. And the integral of W with respect to the Lebesgue measure is greater than the integral of U with respect to the Lebesgue measure to the power lambda, integral of V with respect to the Lebesgue measure to the power 1 minus lambda. So that's the so-called Prekopa-Landler inequality, which is very classical and has a lot of applications. Okay, very, very useful result. Okay, so the way that this inequality is proved is, first of all, you have to consider the case n equals to 1. So you prove this on the real line. And once you have this result on the real line, you just use induction on n. Okay, and the induction on n is actually an elementary step. I would recommend to try it even without looking at the notes. But the case, so the starting point in this induction, n equals to 1, is where we use the Brutebinkowski inequality on the real line. Okay. And the way we use it is, first of all, we notice that the condition here on these three functions, okay, it's homogeneous to truncation and rescaling. Okay, so first of all, if you have this condition, you can assume first that the functions are bounded, because once you have this condition and you take arbitrary parameter, large number m, okay, then if you truncate this function at the level m, you still have the same relationship. So you can write that w evaluated at this convex combination, right, minimum of w and some constant m, so you truncate it at m, will be also greater or equal than u of x truncated at m to the lambda v of y truncated and at m to the 1 minus lambda. Right? So you simply, if you take a minimum on the right hand side between your function and m, then of course automatically on the left hand side you will also have something which is less than m. And then if you can conclude that for these truncations the theorem works, so the integral of w minimum with m is greater than the integral of this truncation of u to the lambda and then truncation of v to the power 1 minus lambda, then you can conclude by letting m go to infinity and using monotone convergence theorem. Right? So first you can truncate and you can assume that your functions are all bounded. It's enough to consider this case. Okay, so let's say that here we notice that it's enough to truncate our functions or consider bounded. And the second thing that we notice is that you can perform the scaling because the result is homogeneous to the scaling. Namely, if you take your function u and scale it by some positive constant, okay, and then you take v and scale it by another positive constant, then to preserve the inequality in the assumption, you just have to rescale w by c1 to the lambda, c2 to the 1 minus lambda, right, for some positive constant c1, c2. And then if you apply the conclusion to these functions, then you can again remove this scaling in the inequality for the integrals. Okay, so as a result, now without loss of generality, we can assume that first our functions are bounded. The sup norm of u and the sup norm of v is first bounded. Now we can also notice that we can also assume without loss of generality that the sup norms are strictly positive. Because if your functions u and v are equal to 0, there is nothing to prove. In the inequality, in the theorem, on the left hand side you would have 0. So you can assume that your functions are non-zero, and as a result, by rescaling, you can, without loss of generality, scale so that the sup norm of u and v is equal to 1. And for any parameter a between 0 and 1, if you take a strictly less than 1, the sets where u is greater or equal than a is not empty, okay, and the set of points, let's say y, where v of y is greater or equal than a, is also not empty for a between 0 and 1. Okay. And if we denote these sets, let's say a and b, now we are going to apply the Brunkowski inequality on the real line to these sets. Okay, in particular, the Lebesgue measure of we're actually going to apply this inequality to the set lambda a and 1 minus lambda b. Okay, so we want to use that gamma of lambda a plus 1 minus lambda b is greater or equal than gamma of lambda a plus Lebesgue measure of 1 minus lambda b. And because we are on the real line, when you scale your set by a constant, the measure, the Lebesgue measure is scaled by a constant. So this is just lambda Lebesgue measure of the set A plus 1 minus lambda Lebesgue measure of the set B. Okay, so here is where we used the Brunkowski inequality. And then if you consider this set on the left hand side, lambda A plus 1 minus lambda b, we actually want to notice here that it will be inside the set, let's call it C, where the function w is greater or equal than a. Okay? And this is where our assumption on this three function, this relationship between these three functions is used, right? Because if you take a point x in A, this just means that u of x is greater or equal than a. And then you take a point y in B, that means that v of y is greater or equal than a. And then if you take their convex combination, lambda x plus 1 minus lambda y, and you plug it into a function w, right? Our condition was that this will be greater than u of x to the lambda v of y to the 1 minus lambda. And because on A, u of x is greater than equal than a, and on B, v of y is greater or equal than a, you get that the w on a convex combination will be greater or equal than a. Right? So in particular, this lambda x plus 1 minus lambda y will be in this set C. And so combining the Brunkowski inequality with this assumption or this relationship between these three functions u, v, and w, we get that the Lebesgue measure of the set C, so that's where the function w is greater or equal than a, right, is greater or equal than lambda times Lebesgue measure of the set A, that's where u is greater or equal than a, plus 1 minus lambda Lebesgue measure of the set where v is greater or equal than a. Okay, so now what remains is just to integrate both sides with respect to a between 0 and 1. And here we should also notice that by the truncation, we can also assume that w is bounded by 1. Since u and v are bounded by 1, truncating w at 1 does not affect the assumption above. So when you integrate, let's say, the left-hand side, the measure that w is greater than a with respect to a, of course, here we can use our usual observation that integral of the tail of the measure, it's equal to the integral of the function with respect to the measure. So this is the same as integral on the real line of the function w with respect to the Lebesgue measure on the real line. Okay, this is exactly the same observation as we always use, that the expectation of a non-negative random variable can be written as an integral of its tail. Okay, so only in this case the measure is the Lebesgue measure and the random variable is this function w. Okay, and of course the same applies to u and v, and so if you integrate with respect to a on both sides and use this change of variables here, then you get the inequality that integral of w with respect to the Lebesgue measure, let me just write dx here, is greater or equal than lambda integral of u plus 1 minus lambda integral of v. And what remains to use is just the arithmetic geometric mean inequality, right? That this average here is, this arithmetic mean is greater than the geometric mean, that integral of u to the lambda times integral of v to the power 1 minus lambda. Okay. And so this concludes the proof of the one-dimensional case n equals to 1. Then one can just use induction on n to prove this for all n. Okay, so that finishes the proof of this Prekopa-Landler inequality. Okay, one of simple and kind of classical applications of Prekopa-Landler is actually a proof which I leave in the exercises of Brutebinkowski inequality on Euclidean space. Right? So we have the analog of the Brutebinkowski inequality that we mentioned on the real line. Now there is an extension of this inequality on Rn, which says that, well, the Lebesgue measure gamma on Rn of a plus b, so it's a n-dimensional volume. Now if you take it to the power 1 over n, then you have the same inequality. It's greater than gamma of a to 1 over n plus gamma of b to 1 over n. Okay, so you have this relationship between volumes of the sum of two sets with the volumes of those sets, and you can prove this using Prekopa-Landler just by taking indicators of the set, okay, which is left as an exercise. One application of this Brutebinkowski inequality is a famous isoperimetry of the unit ball, right? Namely that among all sets with the same volume, unit ball has the smallest surface, right? And you can actually see it immediately from this inequality as follows, that if you consider a measurable set, so take some measurable set on Rn, okay, and then take a Euclidean ball of the same volume. So let B be Euclidean ball of the same volume as A. So gamma of A is equal to gamma of B. Now let's also take a unit ball here. Let D be a unit ball. So in particular, this Euclidean ball of some volume which matches the volume of A will be just a proportional, it will be some constant times the unit ball, whatever the radius C is. And then using this Brutebinkowski inequality, one can show that if you start increasing your set, so if you take epsilon neighborhood of your set A, it will be growing faster, the volume will be growing faster than the volume of the same epsilon neighborhood of the unit ball B. Okay, so in other words, as you start increasing your set and looking at the neighborhood of size epsilon, the volume increases faster. Okay, and so that's the, in some sense, that's the definition of the surface, right? The derivative of how the volume increases will be the surface of your body. So the surface of A will be bigger than the surface of the unit ball. Okay, but even if the surface is not kind of defined in the usual calculus sense, this inequality reflects this idea that the surface of A is bigger than the surface of B. Okay. And the way that you can see this inequality is very straightforward. Here is when you look at this epsilon neighborhood of A, this is the same as adding epsilon times the unit ball. You're basically adding a ball of radius epsilon to each point, right? So that's the sum of these two sets. And by Brutebinkowski inequality above, you can write that this is bigger than the volume of A to the 1 over n plus the volume of epsilon d to the 1 over n to the power n. Okay. Now, of course, in n dimensions, when you scale your body by epsilon, the volume scales by epsilon to the n. So you can also write this as, well, first of all, gamma of A is the same as gamma of B by the choice of that Euclidean ball. And in the second term, you can just take epsilon outside, just by the way the volume scales in n dimensions. Now the same in the first term. If the ball B is C times the unit ball, you can also take this C outside. So you will get C plus epsilon times gamma of the unit ball to the 1 over n to the n, right? So that will be C plus epsilon to the n times the volume of the unit ball. And again, this is, you can take the C plus epsilon inside the volume, so this will be the volume of C plus epsilon times d, which is exactly the Euclidean ball B plus epsilon d. So that's the epsilon neighborhood of this Euclidean ball B. Okay. So that proves the inequality above, and this shows that Euclidean ball has the smallest surface among all measurable sets of the same volume. Okay, and then a little bit later in the proof of the Gaussian concentration, we will see another application of this Prokopov-Landler inequality. All right, so the next object that we need to define is the so-called entropy and Kullback-Leibler divergence between measures. Okay, so the next definition will be entropy and Kullback-Leibler divergence. All right, so here we consider some probability space, a measurable space omega with probability p on it, and then consider some non-negative function on this space, measurable non-negative. Okay, then what is called the entropy of this function with respect to this measure p is the following expression. Okay, it's the integral of u log of u with respect to p minus integral of u times log of the integral of u. Now, here we have some conventions that, you know, if the function u is 0, we do not integrate over that part, so 0 log of 0 here is understood as 0. And then we can either assume that the first integral is finite, u log of u, or we can assume that maybe the integral of u itself is finite, so that the second term is well defined, and in the worst case the first term might be infinity. Now, of course, we will notice in a second that, or we can mention it right away, that this entropy is non-negative, right? This quantity that we define by Jensen's inequality, it's non-negative because the function u log u is a convex function. So you compare the integral of that function minus the function of the integral. Okay, so that's the definition of the entropy of a function u with respect to some measure p. And then the special case will be in the case when this integral of u is equal to 1. So in this case, we can think of this as a Radon-Nikodym derivative or density of another measure. So we can think of some other probability measure q such that its density with respect to p is this function u, right? So q will also be a probability measure on this space under this assumption that integral of u is 1. And so, and of course the other way around, if you have a measure q which is absolutely continuous with respect to p, you can take its Radon-Nikodym derivative and just take this u to be that Radon-Nikodym derivative. And in this case, the entropy above is called Kullback-Leibler divergence. Okay, and it's denoted as dQp. Okay, so this is a Kullback-Leibler divergence in the case when Q is absolutely continuous and has a Radon-Nikodym derivative with respect to P. And this Kullback-Leibler divergence, well, in this case, first of all, the second term disappears because integral of u is 1 and log of 1 is 0. So you only have the first term, integral of u log u with respect to p. And you can conveniently rewrite this as integral of log of u, so dq dp with respect to measure q, right? Because in this definition, u dp is dq. Okay. So the integral of the log of the density with respect to q is the so-called Kullback-Leibler divergence. And again, this is just a special case, so by Jensen's inequality, this will be non-negative. And in fact, the only case this divergence can be 0, right? If you look at Jensen's inequality, in the Jensen's inequality, the inequality will be strict unless your function u will be constant with respect to the measure p, right? Unless u is a constant p almost surely. But in the case of the density, this just means that q is equal to p. So if it's a constant, the density must be equal to 1, p almost surely. And so the only way you can have this divergence equal to 0 if these are the same measures. And so although this quantity is not a metric, it's not even symmetric. I mean, it's defined relative to this measure p, and you have the restriction that q must have a density with respect to p. This can be viewed as some measure of similarity between these measures p and q. Alright, so these are just the definitions, and what we will need is the following classical representation of the entropy as a variational, by some variational formula. Okay, so this is called variational representation of the entropy, and it says that the entropy of a function u can be written as a supremum of integral u times v with respect to p over all functions v. So you take supremum over functions v that satisfy the following inequality, that the integral of e to the v with respect to p is bounded by 1. And the proof of this is pretty straightforward. You just kind of use a standard Lagrange multiplier type argument, and you can show that this supremum will be achieved on some explicit function v, and when you evaluate on that function v, you get exactly the entropy. Okay, so in particular, this variational representation for the case of Kullback-Leibler divergence, so when u is the density of some other probability measure q with respect to p, the way we will use this representation is the following, that if integral of e to the v with respect to p is less than 1, then this implies that the integral of u times v with respect to p is less than or equal than the supremum over such functions. So it's less than or equal than the entropy, which in this case is the divergence. Moreover, since u is this density of q, it's the same as integral of v with respect to q. In other words, if integral of some function v, of the exponential of some function v with respect to p is bounded by 1, then automatically the integral of that function with respect to measure q is bounded by this divergence quantity d. Okay. So we'll use this variational representation in this particular way. Okay. And right now we have all the tools to prove the Gaussian concentration inequality here in combination with the Kantarovich-Rubinstein theorem from the previous section. So we will move on now to the application of these inequalities and the Kantarovich-Rubinstein theorem.